Imagine, glass that once shattered into deadly sharp fragments now saves lives. How did humanity transform a fragile substance into armor for a car? And what is hidden behind this seemingly simple transparency? Every year, over 100 million square meters of automotive glass are produced worldwide, enough to cover the area of an entire country. But the real magic happens where molten stone is transformed into a perfectly smooth surface, in furnaces that reach temperatures of over 2,700 degrees Fahrenheit. How did ordinary quartz sand become the foundation of safety technology, without which we cannot imagine modern transport? Watch until the end, and you will learn what accidental experiment changed the history of automobiles forever. The history of automotive glass production is closely linked to the development of the automotive industry, which emerged at the end of the 19th century. The glass used in cars today has come a long way in improvements, making it safer, stronger, and more functional. When the first cars began to appear, they were initially not equipped with glass at all. The open body design only partially protected passengers, and dust, wind, insects, and other hazards made trips very uncomfortable. Later, as cars became faster, the need to install protection for the driver and passengers arose. The windshield began to be made from ordinary window glass, which, although it provided some protection, had a serious drawback. During accidents, it shattered into large, sharp fragments, leading to numerous injuries. The first revolutionary discovery in the field of automotive glass was the creation of laminated glass. This happened by chance. In 1903, the French chemist Edouard Benedictus accidentally dropped a flask with a nitrocellulose coating. The glass cracked but remained whole thanks to a thin layer of plastic. This accident inspired the scientist to create multi-layered glass, which later became the basis for triplex. Already in the 1910s, laminated glass began to be used in premium class cars. Its construction consisted of 2 layers of glass, between which a thin, transparent film was placed. In the event of an impact, the glass did not shatter, and the cracks remained on the film. In the 1920s, laminated glass began to be actively used in the production of windshields. Its main advantage was increased safety. Even during serious accidents, the fragments did not fly apart but remained in the polymer layer. The next stage in the development of automotive glass came in the 1930s, when the technology for producing tempered glass was patented. This material was produced by heating glass to high temperatures followed by rapid cooling. As a result of this process, the glass became stronger, and when it broke, it disintegrated into small pieces with blunt edges, which minimized injuries. In the mid-20th century, tempered glass began to be used for the side and rear windows of cars. It was cheaper to produce compared to triplex and provided a sufficient level of safety for these parts of the car. In the 1950s and 60s, automotive glass became even more perfect thanks to the development of technology. During this time, various important changes took place. Improvement of triplex. The development of new polymer films made laminated glass more transparent, resistant to ultraviolet radiation, and durable. Mass production. The automation of production processes allowed for a reduction in the cost of automotive glass, which made it more accessible to the mass market. Sun protection coatings. For the first time, special coatings began to be used that blocked ultraviolet light and reduced the heating of the car's interior. One of the most important technological breakthroughs in glass production was the invention of the float method in 1959. This technology, developed by the British company Pilkington, allowed for the production of perfectly smooth glass by spreading the liquid glass mass over the surface of molten tin. Thanks to this method, glass became more uniform, strong, and accessible for mass production. The float method is still the basis of automotive glass production today, ensuring its precise dimensions, surface smoothness, and high quality. In the second half of the 20th century, automotive glass underwent even more changes aimed at improving safety and comfort. In the 1960s, heating filaments began to be installed in the rear windows of cars, which prevented fogging and freezing of the glass. In the 1980s, glass with special metal coatings appeared, which reflected sunlight and reduced the heating of the interior. Glass with ultraviolet protection. Thanks to the introduction of new technologies, automotive glass began to provide almost complete protection against harmful radiation. And then we begin the modern period of automotive glass production, which we will talk about now. And we will start with glass for cars. Automotive glass is divided into several types depending on its purpose and production technology. Windshield. Usually this is multi-layered glass, which consists of 2 layers of glass, between which a polymer film is located. Such a design ensures that upon damage, the glass does not fly into sharp fragments. Side and rear glass. Most often this is tempered glass, which upon impact breaks into small blunt-angled pieces, which reduces the risk of injury. Panoramic roofs or other special types of glass. Laminated or tempered glass with a special coating for protection against ultraviolet radiation is often used. The main components of glass are natural materials that are mixed in certain proportions to obtain the desired properties. Quartz sand is the main component of glass, which ensures its transparency. It must be extremely clean and contain a minimum of impurities. Soda is added to lower the melting temperature of the glass. Lime improves the mechanical stability and chemical properties of the glass. Additional additives used to correct color, transparency, resistance to ultraviolet light, and other properties. The raw material is cleaned, dried, and crushed to a uniform state. It is important that impurities that can affect the quality of the glass are maximally eliminated. After preparing the raw material, it is loaded into special furnaces for melting. This stage includes several important moments. Let's look at them together. Melting temperature. A temperature of about 2,732 degrees Fahrenheit is used to form the glass mass. In the melting process, the raw material turns into a uniform viscous liquid. Homogenization. The glass mass is mixed for an even distribution of components. This is important to avoid air bubbles or inhomogeneities in the finished product. Furnaces for melting glass are equipped with modern temperature control systems and process automation, which ensures high quality of the final product. After melting, the glass mass undergoes a forming process, which in modern production is most often performed using the float method technology. Feeding the glass mass, the liquid glass flows out of the furnace and onto a bath of molten tin. Thanks to the high density of tin, the glass mass spreads evenly over its surface. Under the influence of its own weight, the glass forms a perfectly even and smooth surface. By gradually lowering the temperature, the glass acquires hardness. At the exit of the bath, it can already be processed. The float method allows for the production of glass sheets with precise geometric parameters and high surface quality. After cooling, the glass sheets are cut according to the dimensions required for automotive production. Automated cutting machines ensure the accuracy of the work. To prevent the formation of cracks and chips, the edges of the glass are ground. Each sheet is checked for defects, such as microcracks, bubbles, or other damage. Next, to ensure the strength and safety of automotive glass, it is subjected to a tempering process. The glass is heated to a temperature of about 1,112 degrees Fahrenheit. Then, the surface of the glass is rapidly cooled by streams of air, while the inner layers cool more slowly. As a result, stress is created, which increases impact resistance. Tempered glass, when destroyed, breaks into small, safe fragments, which minimizes the risk of injury. Next, for the windshield, triplex is used, a construction of glass and polymer film. Its production includes several stages. Joining the layers. A polymer film is placed between 2 glass sheets. The construction is placed in a vacuum press to eliminate air bubbles. Next, the glass is heated in an autoclave to a temperature of 284 Fahrenheit under high pressure. This ensures a strong connection of the layers. Triplex has high impact resistance, and upon damage, it remains in the polymer film, which ensures the safety of the driver and passengers. Next, to improve the properties of automotive glass, various coatings are applied to it. Anti-reflective coatings reduce glare from the sun or headlights of other cars. Ultraviolet protection. Special layers block harmful ultraviolet radiation. Hydrophobic coatings. Ensure that water runs off the surface of the glass. Heating elements. Thin heating filaments can be embedded in the windshield, which facilitate the removal of ice or fogging. To achieve the desired shape, special thermoforming installations are used. The glass is heated to a temperature at which it becomes plastic and is formed according to the given parameters. And so, we have reached the final stage. During it, each product undergoes a thorough check. Transparency and the presence of defects are checked. Next, the glass is tested for impact resistance and endurance to loads. Compliance with standards. The accuracy of dimensions, shape, and other parameters are checked. Then the finished automotive glass is packaged in such a way as to avoid damage during transportation. It is delivered to car factories or service centers, where it is installed in vehicles. The production of automotive glass is a high-tech process that combines physics, chemistry, and engineering. Thanks to modern technologies and strict quality control standards, automotive glass ensures safety, comfort, and durability. And just imagine how many stages the automotive glass had to go through for us to be able to monitor safety on the road and have the opportunity to admire the wonderful landscapes. It seems incredible to me. And you? Every year, over 50 million tons of batteries are discarded worldwide, from small AA batteries to giant electric vehicle batteries. Imagine a mountain of metal reaching the size of Mount Everest, filled with toxic substances. But now, part of this mountain gets a second life. Behind the thick walls of factories, old batteries are put into shredders where steel blades tear them apart. They are frozen with liquid nitrogen and turned into a black powder that will once again become lithium or cobalt. Watch until the end. You will see how a new future for energy is born from waste. Battery collection starts with people. Private individuals turn in batteries from phones and laptops. Car service centers, batteries from electric vehicles, and also businesses that use a lot of equipment. Collection points are in electronics stores, supermarkets, or specialized collection centers. Here, everything is as manual as possible. People bring batteries, and staff or volunteers accept and record them. Old batteries from factories or car service centers are delivered by trucks to large collection centers. Special battery containers have sensors that determine the fill level. When a container is almost full, a signal is sent to the collection company. Some companies use drones to check the fill level of large containers in remote locations. Batteries are sorted by type by people and machines, because batteries come in different types: lithium-ion, nickel metal hydride, lead acid, and so on. They cannot be mixed during recycling. At small collection points, for example, in cities, batteries are sorted manually by workers. They rely on markings, labels, and appearance such as shape and case color. Small batteries from smartphones or laptops go in one direction, and large batteries from electric vehicles in another. At large enterprises, automatic sorting lines are in operation. Machines scan batteries by size, weight, and the type of metals they contain. X-ray analysis or spectroscopy is used to determine exactly which battery is in front of the machine. After scanning, the batteries move along a conveyor to different bins, where they await the next stage. Even at automated factories, people are present. Operators check whether the machines are sorting the batteries correctly. If a problem arises, for example, a torn battery case or a missing label, people intervene and sort manually. Batteries from electric vehicles or solar stations are too large for automatic lines. This is where robots come into play, helping to disassemble these giant blocks into smaller sections. Then they are sorted by material. No matter how much machines do, people are still the most important in the sorting process. These are mainly the workers at collection points and the operators of sorting lines. Specialists assess damaged batteries manually because machines cannot yet recognize all defects. Machines work faster, but for now, they can't do without people. Ultimately, every correctly sorted battery is a chance to recover rare earth metals and reduce environmental harm. Next, the batteries need to be shredded. They enter real metal jaws. The batteries are loaded into a machine that looks like a huge shredder, equipped with steel blades. The blades are so powerful that they can even shred the body of an electric car. Metal chaos ensues. The sound of tearing, grinding, and cracking. The batteries are literally ripped to shreds. Since the batteries can be charged, they first undergo freezing in liquid nitrogen. This cools the metals and reduces the risk of ignition. Some shredders operate in sealed chambers with inert gases to exclude contact with oxygen. There is also a more spectacular option. In some places, a controlled current is first used for ignition. The battery literally burns out, leaving only the metals. The batteries are shredded into pieces from a few centimeters to a crumb, depending on the type of shredder. The blades rotate at a speed of over 2,000 revolutions per minute, and metal fragments fly in all directions with a clang inside a protected chamber. The shredded pieces pass through magnetic separators, which, with filigree precision, extract ferromagnetic metals, for example, nickel or cobalt. Fragments of other materials continue their journey along the conveyor. A fine black powder, known as black mass, settles in special containers. This is where the treasures are hidden: lithium, cobalt, manganese. Machines literally suck up the powder with dust collectors to gather even the microparticles. Residues that are not suitable for recycling, meaning plastic and traces of electrolytes, are washed away with special streams of liquid. At this stage, hydraulic crushers are used, which turn the remnants into a slurry that is easy to filter. Engineers monitor the condition of the shredders and the temperature level inside the chambers. Specialists work with the results of the shredding. They check whether all the metals have been separated and whether any extra impurities remain. If a battery is charged and has defects, it can literally explode during shredding. But the system controls this. The explosion is extinguished by gases, and the process does not stop. After the batteries are shredded and that precious black powder is obtained, science in action, as they say, begins. The metals that seem to be hidden forever are extracted using two main methods: hydrometallurgy and pyrometallurgy. And although this may sound a bit technical, the processes themselves are extremely interesting. So what does it look like? Battery fragments are immersed in special acid solutions. There are huge tanks where a yellowish-green liquid is bubbling. This could be sulfuric or hydrochloric acid. During immersion, a reaction occurs. Lithium, cobalt, nickel, and other metals literally dissolve in this soup. To extract the desired metal, a clever trick is used: ion extraction. Special reagents, for example, organic compounds, are added to the liquid, which capture a specific metal, like a magnet. As a result, each metal settles into a separate layer. When the metals are separated, they are precipitated in the form of salts or hydroxides. They look like small white or colored crystals. For example, lithium precipitates as lithium carbonate, a powder that looks like fine sugar. Cobalt becomes a bright blue precipitate, and nickel, a pale green one. If hydrometallurgy is a gentle approach, then pyrometallurgy is more like shock therapy for metals. Here, everything literally burns and melts. The black mass is loaded into a huge arc furnace, where the temperature reaches almost 3,000 degrees Fahrenheit. The metals melt into a liquid mass, and the plastic and other residues simply burn up. The metals stratify, like oil and water, but at the temperature of molten lava. Several layers form in the furnace. Heavy metals, meaning cobalt and nickel, settle to the bottom, while lithium remains in the slag. This is the upper, lighter layer. Then this slag is broken up and processed separately to extract the lithium. After cooling, the metals take the form of small ingots, shiny, smooth, and ready for reuse. The cooling after the pyrometallurgical process usually happens in a controlled manner. After all, if you just let the molten metals cool on their own, it could take hours and sometimes even days. In addition, such cooling can create an uneven metal structure. This will affect the quality of the final product. Therefore, they are usually cooled in special chambers, where the cooling rate can be regulated. If the controlled cooling is air-based, the ingots are left on a conveyor under powerful fans. It's like a giant hairdryer that quickly cools the metal surface. If it's water cooling, for a faster process, the metal ingots can be immersed in a bath of water or special liquids. This is a huge tank where the red-hot ingot, upon entering the water, releases clouds of steam. It looks quite spectacular. Sometimes there is combined cooling. This is when some stages begin with air cooling and then are completed with water cooling to reduce stress in the metal. Controlled cooling ensures a uniform structure of the metals, which is critically important for their reuse in batteries. This reduces cracks or defects that can arise from sharp temperature changes. The obtained lithium is used to create new batteries, those that will charge electric cars or even your phones. Nickel can become part of turbines that generate energy from wind, and cobalt, an important component of medical equipment. So we are literally closing the loop. Old batteries give life to new technologies. Discarded batteries can turn into a real environmental disaster. First, they contain toxic substances that pollute the soil and water. Second, the mining of new rare earth metals not only depletes natural resources, but also harms the environment. Recycling solves both of these problems. You know what else is cool? The more batteries we recycle, the less we depend on mining new materials. This is a direct path to sustainable development. Despite the popularity of lithium, only 1% of this metal is currently recycled. The main reason is the high cost and complexity of the process. But researchers are developing new technologies that could change the situation in the coming years. Interestingly, even now, electric car manufacturers like Tesla, Volkswagen, and BMW are investing in their own recycling plants to maintain control over valuable materials. Every year, humanity creates energy that on one hand saves cities, and on the other, hides an incredible story of transformations. One average reactor produces 1,000 megawatts and requires only 27 tons of enriched uranium per year, the weight of 3 school buses. But to get these 27 tons, you have to mine and process over 100,000 tons of ore. In this video, we will follow the path from a noisy mine and acid vats to supersonic centrifuges, furnaces, and tiny fuel pellets. Every step is chemistry, giant machines, and unexpected risks that you are almost never told about. Stay until the end, and I will reveal one secret to you that will change your perception of atomic energy. An average American nuclear reactor has a capacity of about 1,000 megawatts. For it to operate for 1 year, it needs approximately 27 tons of enriched uranium fuel. 27 tons is the weight of about 3 school buses. And now let's compare. To produce the same amount of electricity, a coal-fired power plant needs to burn over 3 million tons of coal. That's over 10 million barrels of oil. Nuclear fuel is the highest form of energy concentration that humanity has ever created. But to get these 27 tons of fuel, you need to start with a much larger amount of raw material. The chain of transformations is simply staggering. To produce those same 27 tons of enriched uranium fuel, you need to start with 215 tons of uranium concentrate. And to get those 215 tons of concentrate, you need to mine and process over 100,000 tons of uranium ore. Imagine a giant mountain of stone, the size of a multi-story building, which ultimately turns into a volume of fuel that fits in one truck. This shows how dispersed uranium is in nature and how complex the process of its concentration is. It all begins in the roaring chaos of a uranium mine. Imagine a deep shaft or a giant open-pit quarry where huge machines with a deafening roar bite into the rock. The air here is thick with dust, and every stone that is brought to the surface looks absolutely ordinary, just a gray, dull granite or sandstone. The uranium here is invisible. It is dispersed in the rock in the form of tiny microscopic inclusions, and its concentration is incredibly low, often less than 1%. This means that to get 1 pound of uranium, you need to mine and process hundreds or even thousands of pounds of barren rock. Dump trucks, loaded to the brim, take this ore to a nearby processing plant that hums. The first stop is the primary crusher. This is a giant steel maw that, with a deafening crunch, crushes large stone blocks into pieces the size of a fist. Then, this crushed stone goes by conveyor to a huge mill. A giant rotating drum, filled with steel balls, resembles an industrial washing machine for stones. Here, in a continuous roar, the ore is ground into the finest, grey sand, almost dust. And now the real chemistry begins, a process called leaching. This grey sand is mixed with water, forming a thick pulp, and pumped into huge vats the size of a small house. A powerful chemical solvent is added to these vats, most often sulfuric acid. This acid, like a hungry predator, begins to eat the uranium, pulling it out of the solid rock and turning it into a liquid, dissolved state. This process lasts for many hours, while the entire mixture is continuously stirred. As a result, we get two things. On one hand, tons of wet, now unnecessary sand, so-called tailings, which are toxic waste, and on the other, a murky, greenish-yellow liquid containing our precious uranium. This liquid needs to be cleaned and concentrated. It is passed through a series of columns filled with special ion exchange resins. Imagine this as a high-tech water filter. The resins, like a magnet, pull out only the uranium ions from the solution, letting everything else pass by. Then these resins are washed with another solution, which washes the concentrated uranium off them. And so, finally, our final product is precipitated from this clean, saturated liquid. By adding ammonia or hydrogen peroxide, the uranium is forced to fall out of the solution in the form of a bright yellow, thick precipitate. This precipitate is filtered, dried in furnaces, and at the output, we get the same famous yellow cake, a heavy, radioactive, mustard-like powder. This is the uranium oxide concentrate, the first step on the long path to clean energy. The next step is purification to an absolute, almost unearthly purity. The yellow cake is sent to a special plant, where it is dissolved and, with the help of complex chemical processes, such as solvent extraction, all impurities are removed from it. The goal is to obtain perfectly pure uranium dioxide. But here the main problem arises, which is at the heart of all nuclear energy. In this perfectly pure uranium, 99.3% is the stable, lazy isotope uranium-238, which cannot sustain a chain reaction. And only 0.7% is the energetic, unstable isotope uranium-235, which is our fuel. They are chemical twins, and it is impossible to separate them by chemistry. To make the reactor work, we need to increase the concentration of this energetic uranium-235 from 0.7% to 3 or 5%. To begin enrichment, the solid uranium must be converted into a gas. It is treated with hydrofluoric acid, turning it into uranium tetrafluoride, and then with fluorine to obtain uranium hexafluoride. This is a very corrosive and dangerous compound, which has a unique property. It becomes a gas at a temperature slightly above room temperature. And so this gas, packed in special containers, is sent to an enrichment plant. Imagine a giant, noisy workshop the size of several football fields, filled with thousands of identical, tall, metal column-like devices. These are gas centrifuges. Each of them is a high-tech top that rotates at supersonic speed, making tens of thousands of revolutions per minute. When our uranium gas is pumped inside, the magic of physics begins. The heavier gas molecules with uranium-238, under the action of centrifugal force, are pressed against the walls of the centrifuge, and the very slightly lighter molecules with uranium-235 remain closer to the center. This is a microscopic difference, but it is enough. Special tubes take the gas from the center, which now contains a little more uranium-235, and send it to the next centrifuge in the cascade. And the depleted gas from the walls is diverted to the side. To achieve the required concentration of 3 or 5%, the gas must pass through thousands of such centrifuges. This is an incredibly long and energy-intensive process. When we have finally obtained our uranium hexafluoride, enriched to the required level, it needs to be converted back into a solid material suitable for fuel. With the help of chemical reactions, it is turned into a black powder of uranium dioxide. But this is not just any powder. Each of its particles has a perfectly calibrated size and shape. Now the most interesting part begins, the creation of fuel pellets. This black, heavy powder is sent to a press. Imagine a high-precision pharmaceutical press, only instead of medicine, it stamps radioactive pellets. It compresses the powder with incredible force, turning it into small, dense, perfectly cylindrical granules, or pellets. They are still brittle, like chalk. To give them strength, they are sent to a furnace. But this is not an ordinary furnace. This is a high-temperature furnace, filled with hydrogen to prevent oxidation. There, at a temperature of over 3,000 degrees Fahrenheit, these pellets are baked for many hours. During this process, called sintering, the powder particles fuse together, and the pellet turns into an extremely hard, dense, ceramic-like substance. It becomes so strong that it can withstand the extreme temperatures and pressures inside a nuclear reactor. Each pellet after this undergoes laser control, which checks its dimensions with micron accuracy. The next step is assembly. These small black ceramic candies are carefully, one by one, loaded into long, thin tubes. These tubes, about 13 feet long, are not made of steel, but of a special zirconium alloy called zircaloy. This material is unique in that it is very strong, resistant to corrosion, and most importantly, almost transparent to neutrons, allowing the chain reaction to proceed without hindrance. When the tube is completely filled with pellets, it is filled with an inert gas, usually helium, to improve heat transfer, and hermetically sealed at both ends. Now, it is not just a tube with pellets, it is a fuel element. And the final stage is the creation of a fuel assembly. Several hundred such ready-made fuel elements, for example 17 by 17, which gives a total of 289 pieces, are assembled into one large square bundle. They are held together by special spacer grids. This ready-made assembly, which looks like a giant, high-tech quiver with arrows, is the final product. It weighs about half a ton and is ready for shipment to a nuclear power plant. And so, having passed an incredibly long and complex path from an ordinary stone through chemical transformations, supersonic rotation in centrifuges, infernal baking, and precise, almost clockwork assembly, this concentrated bundle of energy is born, ready to quietly and reliably produce millions of kilowatts of clean electricity for several years. Imagine this. In the heart of the ocean depths, or in the roar of an airplane turbine, there is a part that decides everything. A single shaft, capable of transmitting the power of 1,000 Ferraris, or withstanding speeds of over 10,000 revolutions per minute. But how is this steel axis, which can lift a space shuttle, born from an ordinary cold ingot? And what do a ship's propeller, the size of a 3-story building, and the precision of a jeweler, removing a few grams of metal, have in common? In this video, we will reveal the secret of creating giants, without which neither a ship nor an airplane can move. Watch until the end. A fact that will turn your understanding of the power of metal upside down awaits you. A shaft is a steel rod that transmits colossal power from the engine to the propeller. You can't just take any steel for it. Giant, perfectly clean steel ingots, each weighing tens or even hundreds of tons, are brought to the factory. This is not scrap. It is a special vacuum-degassed alloy from which almost all impurities have been removed. This massive cold cylinder is first sent to a furnace. But this is not a melting furnace. This is a giant heating chamber where, for many hours and sometimes days, the ingot is slowly and uniformly heated to a temperature of about 1,200 degrees Fahrenheit. It becomes dazzlingly yellow, plastic like clay, ready to meet the hammer. And so begins the most brutal and ancient art of metallurgists: forging. A giant crane picks up the red-hot ingot and places it under a hydraulic press hammer. This is a monster capable of dropping its top with a force of tens of thousands of tons, with a deafening, deep boom that makes the ground tremble. The hammer slowly but relentlessly descends onto the red-hot metal. These are not quick strikes. This is a slow, methodical squeezing. After each strike, a manipulator slightly turns the ingot. And so, strike after strike, hour after hour, the formless cylinder begins to stretch and take the shape of the future shaft. This process does not just change the shape, it does something incredible inside the metal. It compacts its crystalline structure and aligns all the grains of steel in one direction, along the axis of the shaft. It's like turning a scattered pile of straws into a tightly twisted rope. A shaft born in a forge will be many times stronger and more resistant to torsion than a simply cast one. After the forge, we have a rough, black, scale-covered blank that only vaguely resembles a shaft. It's time for the sculptor. It is secured in a giant lathe. Imagine a lathe half a football field long. The blank begins to rotate slowly, and a cutter of super hard alloy is brought to it. With a hiss and a screech, it begins to remove layer after layer, turning the black, uneven surface into a perfectly smooth and shiny one. A continuous ribbon of hot, bluish metal shavings, resembling a streamer, comes off the cutter. This process lasts for many days. Computer control ensures accuracy to the hundredths of a millimeter over the entire 30-meter length. Some shafts are made hollow to reduce weight. For this, a perfectly straight hole is drilled through its entire length. After final grinding, the surface of the shaft becomes as smooth as a mirror. Now that the spine is ready, it's time to create its heart, the propeller. This is a completely different story. A propeller has an extremely complex, aero or hydrodynamic shape that cannot be forged. Therefore, it is born from liquid fire, by casting. The main material for marine propellers is not steel, but a special bronze. It is slightly less strong, but it is not afraid of corrosion in salty seawater. First, engineers create a perfect computer model of the propeller. Then, based on this model, an exact full-scale copy is carved from wood or foam. This model is a true work of art. Next, this giant model, which can be as tall as a 3-story building, is buried in a huge pit filled with special molding sand. The sand is carefully compacted around the model, creating a perfect impression of its shape. Then the mold is disassembled, the model is removed, and we are left with a cavity inside the sandstone that exactly repeats the shape of the future propeller. This is our casting mold. Meanwhile, in a giant induction furnace, tons of bronze are being melted. It turns into a liquid, dazzling gold, boiling at a temperature of 1,800 degrees. A huge ladle brings this river of molten sun to our mold, and the foundry workers, dressed in silvery fire-resistant suits, slowly and carefully, through special channels, begin to pour the metal into the sand mold. This is a tense and dangerous moment. The metal must fill every smallest curve of the mold, leaving no air bubbles. After pouring, a long cooling process begins, which can last for weeks. When the metal has finally solidified, the moment of birth arrives. With a roar and clouds of dust, the sand mold is broken, and our propeller is revealed to the world. It is still ugly, black, with a rough surface. It is sent for processing. First, the remnants of metal from the gating system are cut off, and then it enters the maw of a giant 5-axis milling machine. A huge milling cutter, controlled by a computer, for hours, layer by layer, removes the excess metal from the blades, giving them a perfectly precise, calculated aerohydrodynamic shape. But even after the machine, the surface is not perfect. It's time for manual labor. A whole team of workers with grinding machines, like an army of ants, for hours polishes each blade, bringing its surface to a mirror shine. Any unevenness on the surface of the propeller creates turbulence, which reduces its efficiency and causes destructive cavitation. And the final, most important test for both the shaft and the propeller is balancing. They are installed on a special stand and spun. Sensors detect the slightest vibration caused by imbalance. If there is even the slightest deviation, literally a few grams on a multi-ton part, it is eliminated by drilling tiny holes or removing a thin layer of metal. And only when this steel spine and bronze heart are perfectly balanced and fitted to each other are they ready to go to the port to be connected and begin their long service, silently and invisibly rotating in the dark to move giant ships across the oceans or lift airplanes into the sky. The engine of such a container ship can have a power of over 100,000 horsepower. Imagine the power of 1,000 Ferrari sports cars concentrated in one place. And all this colossal energy is transmitted through a single shaft to a single propeller. The torque on this shaft is so huge that if a lever were attached to it, it could easily lift an entire space shuttle. After final processing, the runout of the shaft over its entire length should not exceed a few hundredths of a millimeter. This is less than the thickness of a human hair. Imagine a perfectly straight line the length of a basketball court. Well, the real shaft does not deviate from this line by more than this microscopic amount, and the balancing of the propeller is generally a jeweler's work. On a 100-ton propeller, an imbalance of a few tens of grams is considered unacceptable. It's like finding and removing 1 grain of sand from the surface of a car. The turbine shaft in a modern jet engine, like the General Electric GE90 on a Boeing 777, is not just a rod. Its length is only a few meters, but it transmits incredible power. And the main thing is the speed of rotation. If a marine propeller makes about 100 revolutions per minute, then the high-pressure turbine shaft in a jet engine rotates at a speed of over 10,000 revolutions per minute. At such speeds, the slightest imbalance turns into a destructive force. Therefore, aviation shafts and turbine discs are balanced with an accuracy of fractions of a gram. Imagine a toxic gas that was once used as a weapon in war. Today, however, your plastic windows, the medicines in the pharmacy, or even your drinking water wouldn't exist without it. The United States produces over 12 million tons of chlorine each year, a capacity that could turn the ocean into a giant swimming pool in a matter of days. But the real mystery is something else. Only a tiny fraction of this volume is used for disinfection. So where does the rest go? Watch until the end, and you will learn a secret that will turn your idea of this gas upside down. The United States is one of the world's largest producers of chlorine. Annually, the country's factories produce over 12 million tons of this gas. This number is simply mind-boggling. Imagine the weight of the aircraft carrier Gerald R. Ford, the heaviest warship in the world. It's about 100,000 tons. This means that in a year, American industry produces as much chlorine as 120 such aircraft carriers weigh. This huge amount makes chlorine one of the 10 most produced chemicals in the country. It all begins not in a laboratory, but deep underground. The main ingredient for our recipe is ordinary rock salt, or sodium chloride. But it's not brought to the factory in salt shakers. It is either mined in the form of huge blocks, or, much more efficiently, pumped out from under the ground. Water is pumped into deep underground salt deposits. The water dissolves the salt, forming a saturated salt solution called brine. And it is this concentrated, salty as tears solution that is our raw material. But it's still dirty. It's full of impurities, calcium, magnesium, and other minerals that can clog our expensive equipment. So before the main show begins, the brine undergoes a thorough cleaning. It is passed through a whole series of tanks where, with the help of chemicals, all impurities are precipitated and filtered out of it. At the exit, we get a perfectly clean, transparent, and very salty solution, ready for the main event, electrolysis. Now let's move to the heart of the factory, to the so-called cell room. This is a huge, noisy hall, filled with rows of strange closed tanks, connected by a network of pipes and thick electrical cables. These are electrolyzers, or cells. It is here that all the magic, or rather, all the chemistry, will take place. Let's imagine one such electrolyzer. Essentially, it's a box into which our clean salt solution is poured, and two electrodes are immersed in this solution, a positively charged anode and a negatively charged cathode. And now, a direct electric current of colossal strength is applied to these electrodes. And here the breakdown begins. The salt molecule in the water breaks down into positively charged sodium ions and negatively charged chloride ions, and the electric field forces them to move. The positive sodium ions are attracted to the negative cathode like a magnet, and the negative chloride ions to the positive anode. And here, at the anode, what it was all for begins. Each chloride ion that has stuck to the anode gives up its extra electron. Two such chlorine atoms, having lost their charge, immediately unite, forming a molecule of gaseous chlorine. Billions of these molecules gather together, and tiny bubbles of a greenish-yellow gas begin to appear on the surface of the anode. This is our chlorine. The main resource for chlorine production is electricity. The chlor-alkali industry is one of the largest consumers of electricity in the entire US manufacturing sector. To produce 1 ton of chlorine, approximately 2,500 kilowatt hours of electricity are needed. And now let's multiply this by 12 million tons per year. It turns out that this industry consumes about 30 billion kilowatt hours annually. This is more than the annual electricity consumption of entire states, like Vermont or Wyoming. This is a city of 1 million people, working all year just to break salt molecules. But what happens at the cathode? The sodium ions have arrived there. But they do not turn into metallic sodium. Instead, the electric current splits the water molecules in the solution into hydrogen and hydroxide ions. Bubbles of pure hydrogen are released at the cathode. This is our first byproduct. And the hydroxide ions remaining in the solution combine with our sodium ions, forming caustic soda. This is our second, incredibly valuable byproduct. But here, a huge problem arises. We have just obtained 3 substances: chlorine, hydrogen, and caustic soda. And they must never be mixed. Chlorine and hydrogen together form an explosive mixture. And chlorine and caustic soda react to form bleach, which we don't need at all. Therefore, the whole genius of the technology lies in separating these 3 products at the moment of their birth. For this, special membranes or diaphragms are used. Imagine that between the anode and the cathode, there is a thin, paper-like, but very clever partition. This membrane, made of a special polymer, is like a face control at a nightclub. It lets the positive sodium ions pass through to the cathode, but blocks the negative chloride ions, not letting them into the cathode space. Thus, chlorine is born and collected in one part of the cell, and hydrogen and caustic soda in the other. Now we need to collect our harvest. From the anode chamber, a wet, hot, greenish-yellow gas is continuously pumped out. First, it needs to be cooled. It is passed through heat exchangers, where it gives up its heat. Then, it needs to be dried. Chlorine is incredibly aggressive, especially when wet. It corrodes almost everything. But there is one substance it doesn't touch: concentrated sulfuric acid. So the wet chlorine is passed through towers, where it bubbles through sulfuric acid, which, like a sponge, absorbs all the water from it. The resulting dry, cold, but still gaseous chlorine is ready for the next stage: liquefaction. It is compressed under huge pressure and simultaneously cooled. Under this double blow, the gas turns into a transparent, amber-yellow liquid, similar to oil. This liquid chlorine is much more convenient to transport and store. It is poured into special thick-walled steel tanks or railway cars. Every step of this process takes place in conditions of absolute hermeticity because a leak of this gas is deadly. And what about our byproducts? They are no less important. The hydrogen we obtained is collected, purified, and used either as fuel for the plant itself or sold for the production of ammonia or in the food industry. And the resulting caustic soda solution is pumped out, concentrated by evaporating the excess water, and sold. This is one of the most important products in the chemical industry, used for the production of soap, paper, aluminum, and much more. And so, from simple salt water, by passing a huge amount of electricity through it, people have learned to obtain three extremely important substances at once, which are the foundation for thousands of other products that surround us in everyday life. And now, let's see where all this huge amount of chlorine goes. You might think it all goes to disinfecting swimming pools, but that's just a drop in the ocean. In fact, less than 5% of all chlorine is used for water disinfection. So, where does the other 95% go? It is a key building block for other products. About 40% of all chlorine goes to the production of this universal plastic. The vinyl windows in your house, water pipes, medical IVs, vinyl records, the credit card in your wallet, all of this was born thanks to chlorine. Another 40% is used to create thousands of other organic and inorganic compounds. Pharmaceuticals, solvents, refrigerants, herbicides, insecticides. The list is endless. And chlorine is also a key component for bleaching paper, giving it that same pure white color. And finally, about the byproducts, which are actually no less important. We remember that for every ton of chlorine, we get about 1,100 tons of caustic soda. This means that annually, American industry produces over 13 million tons of this important alkali. This makes chlor-alkali production a perfectly balanced business. When the demand for one product falls, the demand for the other may rise, allowing the plants to operate stably. So these millions of tons are not just statistics. They are proof that this sharp, suffocating gas is the invisible foundation for a huge part of the American economy, from the plastic pipes under our streets to the medicines in our pharmacies. Every year, hundreds of millions of square feet of hollow core slabs are born worldwide. That's an area large enough to build 30 pentagons. Imagine a factory where a machine crawls along a 600-foot track, slowly creating a concrete ribbon half a mile long in a single shift. And now for the main point. These slabs are a whole 2,000 tons lighter for a building with an area of 100,000 square feet. That's a minus 500 elephants on the construction's weight scale. But how can such a light slab be so strong? In this lies the hidden secret of engineers, which you will learn if you watch until the end. The slip former machine crawls along a 600-foot forming bed at a speed of about 4 feet per minute. Doesn't sound very fast. Now let's do the math. That's 240 feet per hour. That's almost the length of an Olympic swimming pool being born from concrete in less than an hour. In a single 10-hour shift, one such bed can spit out almost half a mile of perfectly formed concrete slab. And at a large factory, there can be several such beds. This isn't just construction. It's an assembly line working at a speed unimaginable for traditional on-site concrete casting. And now for the main feature, the hollow cores. These holes inside are not just for aesthetics. They reduce the weight of the slab by almost 50% compared to a solid slab of the same thickness and strength. What does this give us? Here's what. Imagine the construction of an office center with an area of 100,000 square feet. If the floors were made of ordinary solid concrete, their weight would be approximately 5,000 tons. But with hollow core slabs, only 3,000 tons. We just threw out 2,000 tons of excess weight from the building. That's the weight of about 500 adult elephants, which now doesn't need to be supported by the foundations, columns, and beams. This allows for making the entire structure of the building lighter, more elegant, and most importantly, much cheaper. But how can such a light slab be strong? The secret is in those tensioned steel muscles. The concrete used in these slabs is not the same as on your sidewalk. This is high-strength concrete that can withstand a pressure of over 8,000 pounds per square inch, while ordinary concrete is only 3,000 or 4,000. And the steel strands inside it are tensioned with such force that they create a constant compressive force in the slab. Thanks to this, a hollow core slab can easily span a length of 60 feet without any intermediate support. 60 feet is the width of a professional basketball court. Imagine a huge open space without a single column. That's why these slabs are beloved for the construction of parking garages, supermarkets, and open-plan offices. Annually in North America, over 200 million square feet of hollow core slabs are produced. This number is simply mind-boggling. This is an area large enough to build 30 giant buildings like the Pentagon. Every year. This isn't just a building material. This is a whole industry built on speed, efficiency, and the smart use of resources. So these figures are not just dry data. They are proof that sometimes, to become stronger, you just need to get rid of the excess inside. It all begins not in a concrete mixer, but on a giant, perfectly flat airfield inside the workshop. This is a forming bed. Imagine a perfectly smooth, polished steel track several feet wide, but with a length of 400, 500, and sometimes even 600 feet. This is longer than 2 football fields laid end to end. Under this track, pipes are laid, through which hot water or steam circulates to keep it warm. This is our ideal bed for the birth of the future giant. At both ends of this track are massive steel anchors, embedded in a thick concrete foundation. They look like steel teeth that have bitten into the ground, and their task is to withstand simply inhuman loads. Between these two anchors, high-strength steel strands are stretched. This is not ordinary wire. It's several steel threads woven together, each of which can withstand the weight of a car. They are laid along the entire length of the 600-foot bed, forming the future skeleton of the slab. One end of each strand is securely fixed in the anchor, and, to the other, a giant hydraulic jack is connected. And this jack begins to pull. It tensions each of these steel strands with a force of 30 or 40,000 pounds. It's like hanging 3 full-size pickup trucks on each thin thread. The steel muscles tense up, becoming as hard as the strings of a giant guitar, and store colossal energy within them. This is secret number 1. Pre-stressing. When the steel skeleton is tensed and ringing from the tension, the main hero comes on stage, the forming machine, or slip former. This is one of the most amazing machines in the world of construction. Imagine a strange, low-slung, self-propelled creature that slowly crawls on rails along our long bed. On top of it is a large hopper where concrete is loaded. But this is not ordinary liquid concrete. This is so-called zero-slump concrete. It is so dry that it resembles damp earth. If you took it in your hands, it would not flow. And so this machine begins its slow journey. Inside it, a real miracle happens. First, the concrete from the hopper is fed down and surrounds our tensioned steel strands. Second, special vibrators and compactors with incredible force tamp this dry mixture, making it incredibly dense. And third, most importantly, inside the machine are special forming tubes, or mandrels, which, vibrating, pass through the thickness of the concrete, leaving behind perfectly round, smooth, hollow cores. The machine, like a giant concrete snail, slowly crawls forward, and behind it, like a trail, remains a perfectly formed, endless concrete slab, with hollow cores inside and tensioned steel muscles hidden in its body. Because the concrete is so dry, it instantly holds its shape and does not spread. This is secret number 2. The hollow cores that make the slab 50% lighter than a solid one, while barely reducing its strength, because the main work is done by the top and bottom flanges. When the machine reaches the end of the 600-foot bed, its work is done. But our slab is still green and weak. It's time for a spa procedure. Workers cover the entire length of this concrete ribbon with huge insulating tarps, similar to blankets. Hot steam is fed under these blankets. This creates a sauna effect that sharply accelerates the chemical reaction of concrete hardening. Under normal conditions, concrete needs weeks to gain full strength, and in this hot, humid atmosphere, it reaches the required strength, over 5,000 pounds per square inch, in just 12 or 24 hours. When the concrete has hardened and become as strong as stone, the moment of release comes. Workers slowly release the tension on the hydraulic jacks. The tensioned steel strands, which are now firmly bonded to the concrete, try to contract to their original length, but the concrete does not let them do so. As a result, this huge compressive force is transferred to the concrete slab itself. Now it is not just concrete, it is pre-stressed or compressed. This means that when a load is applied to it from above, trying to bend it, it will first have to overcome this built-in compressive force. This is what allows it to span huge distances without additional supports, and the final act of this spectacle is cutting. Along our long concrete ribbon, a giant saw moves on rails. This is a monster with a huge disc coated with industrial diamonds. With a deafening roar and a fountain of sparks and water that cools the disc, this saw with incredible precision cuts the slab into pieces of the required length according to the order. The finished, perfectly even, light, and incredibly strong slabs are picked up by giant cranes and loaded onto trucks. And so, having passed the path from a tensioned steel string to the slow crawl of a concrete snail and the final diamond cut, this brilliant work of engineering is born, ready to become a fast, effective, and reliable floor in the buildings where we live, work, and play.